Okay, so I mean, thanks a lot for having me. And hi everyone. So I'm Kruno. I'm a PhD student in Paris, in France. And maybe it's better if I do my introduction slide. So you can see my screen, right?
Yep.
Okay, so basically I'm a PhD student at ENS Paris and with Meta as well. And I'm jointly supervised with Jacob Verbeek at Meta and Giulio Biroli at ENS. And I'm basically working on the intersection between theory and practice, and we're trying to analyze models like diffusion, generative models in general, like diffusion models and flow matching. And today I'll briefly be going through one of our recent papers, which basically analyzes classifier-free guidance. And this is also joint work with Mark Mezar, who is now at Bocconi. So basically, what I'm going to do is I'm going to give a quick overview of diffusion and the dynamical regimes of diffusion. I'm going to then talk about classifier-free guidance a bit briefly. Um, I'm going to talk about its effects. I'm going to get into some theoretical analysis. I'm not going to go that deep into theory, but like if anyone's interested, please feel free to just interrupt me and ask. And I'll talk about some empirical evaluations. And yeah, at any point, like if something's unclear or like something, just like please feel free to just raise a hand or whatever. Okay, so the standard process of diffusion, I'll just briefly go through, even though I'm sure like everyone here is like well aware already. So I'm gonna be using the classic forward process, which is described by the Ornstein-Uhlenbeck process, which is terminated at some large time TF. And then this time TF, basically all the information about the data has been destroyed, and the process can be described as like a standard Gaussian. I'm going to be using this notation here. dBt is going to denote the standard Brownian motion, and xt is going to be a Gaussian distribution with a certain mean and a certain variance. And basically the whole kind of challenge and the beauty of diffusion models is in learning the backward process. In this, basically to learn this equation, we need to learn this score function. I'm going to be denoting it like this, and basically the score function is the gradient of the log probability of x at every time. So we need to learn this for every time for every x. And this is kind of like the standard sketch. So we go from some standard distribution, some data distribution at time t is equal to 0. We noise for capital T steps until we get until we get to this large time, and we want to approximate this process. So basically, what people have done so far is people have analyzed this from like a high dimensional physics perspective in let's say that like in the case where like you start from like an initial distribution, which is a mixture of two Gaussians. And you can, for example, think of this as you know, like being two classes, for example, dogs and cats. And basically then as you noise and you keep noising at some large forward time t, you're basically going to get to a standard Gaussian distribution. So basically what people have analyzed and like theoretically, they have shown that there exist three regimes, but I'm only going to talk about the first two because for the whole presentation, the second and the third regime are exactly the same and there's not going to be any difference. But basically what happens in these two regimes is when we go backwards, so we go from noise to the data, in the first regime, the trajectories of our particles have still not decided which class are they going to end up at. And after this, what they call speciation time, there is probability 1 that we're going to end up in either one of these two lumps. So basically, this speciation time kind of tells you, okay, well, before that, I'm still not sure in which class am I going to end. And after that, with probability 1, I know exactly where I'm going to end. And in this, they analyze this through high-dimensional Gaussian mixtures, and basically to calculate the speciation time, you need to find out the lambda here, which is the eigenvalue of the principal component of the covariance matrix of the data. But there's definitely a lot of works currently working about dynamical regimes, and many works have shown that also these can be found in data that is more complicated, for example, that lives on manifolds, and there's a lot of kind of empirical works in which they see this kind of speciation phenomenon rising. So it's much more kind of broad than just, like high dimensional Gaussians. So this is basically the first kind of introductory part. The second introductory part, I'm just going to briefly mention like classifier-free guidance so that like we're all on the same page. So in this standard backward process formula, here we just use a score. And if we want to generate any point from our data distribution, we're going to use this unconditional score. If we want to condition, for example, on one bump, so like on a dog or a cat on like a class, we're going to use the class conditional score. And what classifier-free guidance proposes is instead of just using the class conditional score that, for example, says, okay, give me one of the two bumps from my sketch, or for example, generate me an image of a dog. Classifier-free guidance is a heuristic that proposes to basically add a push proportional to this parameter omega, that is basically the linear difference between the conditional and the unconditional score. So basically what this says, okay, I want to push further towards the mode of my distribution corresponding to that class. And what this says is I want to push away from the kind of mean of the data, because what you can do is like you can always kind of think as like score functions as some sort of like a force field that is basically pushing you towards the high density regions. And basically using classifier-free guidance has been shown that theoretically in one and low dimensions, the generated distribution is not going to equal to the correct one that we want to generate. And I'm going to get a bit further into this in a second. And basically in practice, what I guess a lot of you have seen is that classifier-free guidance basically results in generated images that have a very decreased diversity and can also collapse to the mode. So kind of like in a standard example of Gaussians, like these are the three Gaussians that we want to get to. And omega being equal to 0 means that we're just doing class conditioning, but we're not doing any guidance. You can see that as omega increases, the mean of each of these bumps or each of these classes is going to be kind of what they call like, is going to be overshot. So basically the mean is going to have larger magnitude than the actual mean. And you can see that like the variance is also going to start to decrease. And you can also see, for example, by just examining one image, not using guidance is not going to give you as kind of crisp images with high fidelity. As you increase the parameter, you're going to get very nicer pictures, but there are some ranges of omega in which basically too strong value can give you some unwanted effects. For example, you can see oversaturation here. So the research goal that we asked in our work is basically, can we use classifier-free guidance to actually generate the correct distribution in large or infinite dimensional settings? Because previous work has shown that in low dimensions, this is impossible. And the second example is, okay, well, if this is possible, can we actually construct some better guidance strategies? And as sort of like a running example, I'm going to basically have this picture of bees. So in the first row, you can see images that we have generated by using a pre-trained diffusion transformer. We just took it off the shelf, we downloaded the weights, and basically we didn't use any classifier-free guidance. We only conditioned on the class corresponding to bees. You can see that like these images are quite diverse, but you can see that like in some of them you get to see some bees. But for example, in the first two images, there's really no bees. But you can kind of think, okay, well, if I went through all 1000 classes of ImageNet, I would have probably kind of guessed that like this was supposed to correspond to like a distribution of bees. But you can see that like images are not that crisp. And then if you look at, for example, at the bottom row, this is obtained by using classifier-free guidance, and we did not, perform some like hyperparameter, like we did not select two large values of omega. We just selected the value of omega that gives, like the best score, like in terms of FID. And you can see that there are bees and they're very crisp, but you can see three problems. The first one is there is a complete loss of diversity. So there are no, for example, like, bees flying. There's like only bees on the flowers. There's no red flower, purple flower, and so on. The second thing that you can see, so each one of these columns basically corresponds to starting from the same seed, which means from the same noise. And basically what this means is that you can see that like there's been a complete loss of semantics. So basically what happened here is this path, starting from the original noise, was basically generated a bee on a blue flower. And this path kind of completely lost, like any sort of like relationship with like where it started. And the third problem, which I'm not going to get into, you can also see that like classifier-free guidance has actually picked up a spurious correlation in which not only has it generated a bee, but also it's generated a yellow flower every time. So this is something that we're going to kind of have as a running example and we're going to try to fix. And just to kind of have like a little side note, basically, because I'm going to be using this plot quite a lot, what I'll be showing here is, for example, if we start a lot of processes which basically start from, let's say, I don't know, like you start somewhere here, and you condition on, let's say, this bump here, you're going to have a lot of paths. And as you basically keep running these paths, they're going to look something like this. And these are going to be the paths corresponding to class conditional but not guided diffusion model. And basically these paths, once I average them, are going to correspond to this line. Sorry, this blue line here. So basically what's been observed in practice is in low dimensions, if you use strong classifier-free guidance, so for example, let's say like we look at like this purple curve here, basically what is going to happen is your paths are very soon going to basically overshoot. At some point, the mode corresponding to this path is going to start to retract and pull it back. But basically, as we've used too much classifier-free guidance, when I average these paths, they're going to end up somewhere a bit higher. So they're not going to generate the correct distribution as the unguided model would. But I'm going to go into this in a second. I just want to kind of make sure that it's clear like what this path is doing. So basically what we're doing is we're sampling a lot of paths using the same kind of guidance value, and we're averaging over them and seeing, okay, well, how does this path basically evolve with respect to the mean of the class that I'm going to? But maybe this is
So
going to be, yeah.
can you, in the chat, we have the question, what is QT? So I
Ah,
suppose this
yeah,
is okay, just go ahead.
I'll get, yeah. So I'll get to that in a second. So basically Qt here is basically I'm taking the x at time t, I project it onto my target mean. So basically I do the dot product between them and I normalize it because this is basically what we had to do in theory. So basically what I do is I just basically plot a normalized cosine or like dot product between x and m. So if this is high, basically it means that we're going like basically the correct value of q is the value that is obtained by using the unguided model. So
What
basically, if
is, what is X and what is M?
yeah, so x is just the particle that moves from Gaussian noise and that should end up at target distribution. So this should say x of t. And m here is basically my target mean. So in my previous example, if I want to end up at this bump here, m is going to be the mean of this Gaussian distribution. Oh, sorry, like the mean of this mode of the two
Okay,
modes.
so in practice, you take in your data set all the data that is labeled as B, and then you take the average of that and plug this into this dot product computation with your XT.
Exactly. Yeah. Okay. So basically what happens in practice and what people have observed is, for example, you can, like here, I plotted again the same bump in blue. So I plotted just one of the two bumps of the Gaussian. If you're in very low dimensions, even if you use a very small value of classifier-free guidance, basically you will never generate the correct distribution. And this is kind of what has been observed. So like you can see here that, like for very small omega, my mean is a bit larger than my correct mean, which is in blue, and the variance or like the standard deviation of the distribution has shrunk. And as I keep increasing omega, basically this effect is going to kind of become worse and worse, and my generative distribution is going to be more and more different to the target one. However, the first thing that we observed kind of like in practice is that if you actually keep increasing dimensions, this effect is going to get smaller and smaller. So, and I'll later come back to this plot again. Basically, current works, especially theoretical works that have tried analyzing classifier-free guidance, have said, okay, well, in one dimension or low dimension, classifier-free guidance is not going to work because it's going to overshoot the mean of the target distribution and it's going to shrink the variance of the target distribution. Now, I just want to make clear that there are still some applications in which having the mean larger and having the variance smaller is beneficial. And in this case, classifier-free guidance can still be beneficial. But from our point of view, where we want to generate the correct target distribution, which corresponds to this just one bump, classifier-free guidance is not going to work. But in large dimensions, however, this effect is going to diminish and we're going to generate it. Now, we wanted to ask ourselves, okay, well, like, why does this happen? Like, what is actually happening? And kind of like to spoil our results, basically we analyzed this score and then we showed that, okay, in small dimension, the correct kind of path, which is the unguided path, if you look at the difference between this path and the paths using stronger and stronger guidances, you can see that these paths are going to diverge at the very beginning. And once they start being pulled by the data, because once they get very close to kind of like the mode of the data that they want to get to, the push has been so strong so far that basically the attraction force of the data was not strong enough to push it where it should end up. But basically what happens in large dimension, you can see that before this speciation time that I mentioned a couple of slides ago, classifier-free guidance is going to push this path stronger, but just before speciation time, actually these paths are going to realign. And what's going to happen further is they're not only going to realign among themselves, but they're going to realign with the unguided path. And after the speciation time, actually classifier-free guidance is not going to have any effect. So this is kind of like the main conclusion, but I'll go into it a bit more. For the sake of time, I'm gonna skip our theoretical analysis, but basically what we show, you can kind of think of it as follows. If you look at the score as a function of x and of t, this is just the gradient of the log probability at time t of x. And this is basically a weighted average of the conditional scores. But the speciation time, as I mentioned at the beginning, is basically a time after which we are 100% sure that we're going to end up in one of the classes. So in the second regime, which means after speciation time, only one of these probabilities is going to be 1. All of them are going to be 0, apart from one, and that is the conditional probability to the class that we're going to end up. So basically what's going to happen is this whole sum is going to turn into one term, and then basically the conditional score is going to equal the unconditional score. So what this allows us to conclude is that basically classifier-free guidance is going to have an effect before speciation time and is going to push you further and stronger towards the correct class distribution. The second result is that we can show theoretically that just after speciation time, all the paths are going to align with the correct unguided path. And after speciation time, classifier-free guidance is not going to have any effect, so we might as well just turn it off. But this is, of course, for theory and for sufficiently large dimension. But I can go into later, like what happens in practice. But yeah, do you have a question?
Yeah, so in your computation or your graphs, could they also be explained like this, let's say the hump and going back up? Could this also be explained by if we have let's say we have your bees, then the mean of it will be at a very low density region. Like if your bees or the bee, the average bee doesn't have high density probably, right? Your M. In dimension 2, your M has high density, and in dimension 200, your M probably doesn't have high density.
So I would say that, yeah, so one of the things is that definitely, if you look at the probability distribution at time t, it is probably, yeah, it's probably not as kind of dense as it is at like a very small time. What I kind of like to think about it more is like you can think about it having like two magnets, and basically one of them is here, the other one is on the bottom, and
No,
basically
but
what's
what the point I want to get to is your QT flawed, this evaluation, and looking at that as a measure of how close you get to one class. Right, you're trying to use this sort of as a proxy as the density of xt conditioned on the class.
Yes. So
And
the thing, so insufficiently, if you have large enough dimension, if you look at the dot product, um, if I'm going towards this class, my dot product is going to basically explode, or like it's going to be really high, which is exactly what's happening here. If you're in the situation which we basically assume in theory, and you assume that, so in our case, we have two Gaussians, and we have to assume that each of the Gaussians is going to be very well separated. So basically, there's going to be very little overlap between the two classes. In this case, unless I'm going towards my correct class, I'm not going to see this. So I'm not going to, so basically, if my paths behave like this, then I'm sure that I'm going towards the correct class.
okay, I'm sure if we go up there, then we're going to the correct class. But I'm trying to understand the hump.
I see.
Why?
So what the
Yeah.
hump here means is, so basically the push was stronger than, so basically you can kind of think about it is like as having some sort of like flow of like your probabilities of like your particles, and your particles want to follow this flow, and this flow is basically going to just look like this blue thing. But if you have some force that is at every time pushing just up, if this force is super strong, at the beginning it's going to make this flow kind of like do this bump, but this basically, what's going to happen is like the push that we're giving with classifier-free guidance, as time decreases, is going to basically get smaller and smaller, and the magnitude of the flow is actually going to get larger and larger, which means that the pull towards the blue one is going to get stronger than this push that that we're having from classifier-free guidance.
Yeah. Okay. Yeah.
And this is basically like essentially exactly what we do in the proof. You just show that like, this pull towards the blue line gets stronger and stronger. It is just that if the dimension is small, the pull is not strong enough to overkill or like to overtake the force of classifier-free guidance.
Alrighty.
Yes.
Yeah, so you guys, I think from the paper, you guys scale the means with like there's proportional to root d,
Yeah.
and then you guys get a speciation time which is like log root d.
Yeah.
Is root d, is there any significance to root d, or is it just if it's just some function of d, then the speciation time is that same function of d? I guess I'm asking like why, like is there like a short intuitive reason that like root d is like the correct way to like scale these means so as to get like some meaningful result about like
Yeah.
why would I do root d?
So
Like I could also just do d or something, and maybe the speciation time would just be like log d. In which case it seems like it's a more general result than having anything to do with root d. Is there any reason that you guys chose root d?
so I think in order to that's basically that's a good question. I should have also mentioned it. Like the speciation time is like we didn't invent speciation time. This is like a previous work of my supervisor. But if I understand correctly, basically, in order to like what you need to have is you need to have that your two Gaussians are well separated. Because if your Gaussians aren't well separated, what's going to happen is like you cannot define a class because you have basically like you can kind of think of it as like having images. Oh, can you hear me?
Yeah.
Yeah.
Yeah, okay. Can you like if you have images of like for example like this image of a bee and the flower, like you do not know actually if this is like an image of a flower or like an image of a bee. Like this could happen the same. So like this could be both. So basically what the assumption of root D does is it's just saying that the magnitude of the means is larger than the overlap of the variance. If my mean was also if my mean was like of magnitude D, then I might be wrong, but I think that the theory should still hold because the only important thing is that these are well separated. It's just that I think when you want separation, you want the separation to be as like kind of like as little as possible, or like kind of like you want an assumption that is like as weak as possible. And I think log D is kind of like the minimum required for this to happen.
I see. Okay. All right, but that's cool. That makes sense. And my second question was, and feel free to skip over this if this comes up later, or it's just like we're, you want to get onto the next slide or something. But I was wondering how, or if you guys thought about how this, like, there's like another limit here, which is like how many modes you have. Because like, I guess in like real world applications, it's not just high dimensions, but it's like you have like way more than 2 modes probably in practice. And
Yeah.
so it's like, how do these results, like maybe like if you scale on the infinite modes limit, and I guess one of the difficult things is that like, it's not clear how you arrange these modes if you have like an arbitrary number of them, like if you put them in a grid or in a circle. But like, it could be that like, maybe you could imagine that if I have a million modes, then the speciation time just like becomes 0 or something. And then like, you just always want to use CFG or something like that.
Yeah. So I'm going to try, hopefully, to answer your question by the end of the presentation. I think it's like a brilliant question. I think like it kind of like pinpoints exactly kind of like the biggest problem, but also like something that I think is basically solvable. Um, if if we have like our theory can straightforwardly extend to any number of finite classes, the only thing that we have to assume is that like each of the bumps corresponding to that class is separated from the other ones. And I think it's kind of, as you said, like if you just assume like having like a, I don't know, like a very large like hypercube, or like if you assume like, you have like some circle, and like each of these modes is like on the circle, but like the circle has a very big radius, then this is something that would kind of be okay, right? Because you would have classes that are very, very separated. The question is, we do not know whether this happens on the manifold of images. And I mean, as you can see here, like there's obviously not well separated class, or like not well separated classes. But luckily, what I think is what is happening, and one of the reasons why our theory, when we kind of like tried analyzing whether it holds in practice and we saw it holds, is if you look at the loss of variational autoencoders, most of these losses, they have like a lot of summons, and each of the summons has, like role in doing something. One of them is like for having a pretty reconstruction. So like you want the MSE between your original image and your reconstructed image to be low, and so on. One of the terms is the term that is responsible for making sure that if there are 2 images corresponding to the same class, that they are embedded close in the latent space. And the other term is basically responsible that if there are 2 images corresponding to different classes, that these embeddings are far. And then not in all of the autoencoders, but in some of them, you can also kind of like impose that basically each of these lumps corresponding to a class is somewhat similar to a Gaussian. But if we just disregard like this last one that I said, the first two, so 2 images of the same class being embedded in the same space, and 2 images being embedded closely, and 2 images of different classes being embedded like in a very kind of like far away, is basically something that is kind of exactly contributing to our assumptions that we have to assume in our theoretical analysis.
Okay, that makes sense. I appreciate your explanation.
Okay, thanks. But I'll try to get to this again. Because I think it's
Okay.
very important, because like we kind of do use this like to kind of show better results in practice, but the question is really like, why does it hold?
Okay.
Okay, so this I already did. So, okay, so just kind of like to do a short recap. We have this speciation time, which is basically saying, okay, after the speciation time, I'm sure in which class I'm going to end up. Before the speciation time, I'm not sure. What we've shown is that in large enough dimensions, classifier-free guidance is only going to have an effect here. And after the speciation time, it's not going to have an effect because our paths have aligned with the unguided correct path. And basically, they're going to generate the same target distribution. So the question that we wanted to ask ourselves is, okay, like, can we actually construct a generalized form of classifier-free guidance? And if we can we come up with a simple form that is basically going to have the same theoretical guarantees, but maybe work better in practice? Because I mean, what I've just told you now is that in small dimensions, we're going to have this overshoot and variance shrinkage. In large dimensions, we're not. But then I've also shown you pictures that basically work in high dimensional spaces, but we still see this variance shrinkage. And there are many different things like why basically classify like why there is like this disconnect between like theory and practice. And I'd love to get a bit more into them like by the end of my presentation if we still have time. But basically we've just asked ourselves, okay, can we basically construct guidances that are going to have all the theoretical assumptions that still to be valid, but basically perform better in practice? And by analyzing our proofs, we propose basically nonlinear classifier-free guidance in the following form. So we still have the conditional score. We still have the difference between the conditional and the unconditional score. But now we have this function phi of t, which is basically the function of the norm of the difference between the two. And you can think of this, okay, well, if this phi of t is just a constant function, if I just fix it to omega, I'm going to get my standard classifier-free guidance. But basically, we can do a lot more. And the only thing that I need to have, the only basically requirement for this phi function is that as we take s times phi of t of s going to 0, this limit has to equal 0. And I'll explain in a second what does this mean. But basically what we did is we looked at the score difference. So this is the norm of the difference of the class conditional and the unconditional score for Gaussian mixtures. And you can see that here for time is equal to 1, I am at a Gaussian noise, and for time is equal to 0, I'm at my data. So basically what I'm going to have is the difference is going to be very small at the beginning because both conditional and the unconditional part start from the standard Gaussian. At some point, this difference of the scores is going to increase, and then at some point it's going to decrease and go back to 0. And why does it go back to 0? Well, you can think about this as once you're very close to the data, if my bumps are separated, the score field, once I'm very close to my data, is going to be exactly the same, whether I'm class conditioning or whether I'm not class conditioning, because I'm guaranteed to end up in that bump. And basically what this limit just says is it just says that basically what I want here is I want to have nonlinear versions for which I'm going to start at 0 and for which I'm going to end up at 0. And basically what we want to do is by what standard classifier-free guidance can do is like it can just multiply basically this difference with some omega, which is going to increase or decrease this curve. But we want to basically have something that is going to also allow us to alter the shape of this curve such that maybe we can get better performance in real world. And one thing also that we did is like we analyze these curves for class conditional models like DIT and EDM from NVIDIA, and also two text-to-image models that have a very similar architecture to stable diffusion. And we observed very similar behavior. So basically what we said is, okay, well, let's take the simplest possible form that's going to satisfy this requirement, and let's just raise this score difference to the power of alpha. And this parameter alpha has to be greater than -1, but it can basically be like anything that's greater than -1. Because what our theory tells us and what we can do theoretically is we can show that when alpha is non-zero, which means that we do not have standard classifier-free guidance, the variance of the target distribution is going to be smaller, and this overshoot that we observed previously is going to be shrunk. And then basically looking back at the same example, this is what we observe. So if you look at each column again, each column starts from the same seed. And what you can see here is basically that each of the images is basically almost exactly semantically the same as the original image. And this is why we kept diversity. But you can also see that basically the details are much sharper and much crisper, which is basically why people use classifier-free guidance. So we've kept diversity. The mean is, I guess, still the same because you can see that like the distributions are very similar, but this crispiness is here. And at a certain cost, this cost is basically the fact that we've introduced an additional hyperparameter, but hopefully I can convince you like in a slide or two that like it's actually not that costly. So basically what we did is we first analyzed, okay, well, is this effect of mode collapse as prominent in our nonlinear proposed version as it is in standard classifier-free guidance? And you can see here that if we condition, so this is again diffusion transformers trained on ImageNet. If we condition on a label that is basically jellyfish, for a weak omega, you're going to see some sort of like reduction of diversity. But if you increase omega to 5, which is not that, like stringent, you're going to see that like the diversity is completely lost. And you're also going to see that like sometimes it collapses to the mode. And I guess the mode of jellyfish is just a blue image of the sea. What you can see in the power law of classifier-free guidance is you can see that like the diversity is much kind of bigger and much stronger. You can also see that like we are much less sensitive to like changing omega. Here we changed omega from 2 to 5 and we saw like a drastic mode collapse. And here we changed omega from 2 to 10 and you can see that like there is some sort of increase in fidelity and the images are crisper, but you can also see that like we've still preserved semantics and we still are far from collapsing to the mode. And another thing that we did is we basically said, okay, let's just look at basically what does increasing alpha, so making it more and more nonlinear, do. And you can see that basically comparing to the standard classifier-free guidance, increasing alpha is basically enabling us to have larger and larger diversity with almost no cost at, like crispness of images. And just kind of as a last empirical analysis of our work, what we did is we analyzed, okay, how do our results change when we vary the standard parameter omega and the nonlinear parameter alpha? So basically here what we plot, and this analysis is for the EDM2 network, also trained on ImageNet. Here we basically look at what happens with FID. So FID, the beta is lower. For alpha is equal to 0, we have a parabola here which basically means that there is, so basically this is going to be the standard classifier-free guidance. And we can see that basically as we keep increasing alpha, which means that like our sampling dynamics are more and more nonlinear, this parabola is basically going to get lower and lower, which basically means that non-linear version of classifier-free guidance is consistently going to be better. But also another thing that we can observe is, okay, well, what if I plot omega on my x-axis? What is going to happen to the parabola for different values of alpha? And what you can see here is that basically for alpha is equal to 0, which corresponds to the standard classifier-free guidance, this parabola is super sharp. And what this means is that it's going to be very hard to find the optimal value of omega because we're going to have to be very careful when we do hyperparameter optimization. But what you can see is like as we increase alpha, not only does the minimum decrease, but also this parabola gets much wider, which is basically in line with the images we saw before, meaning that small perturbations to omega are basically not going to have that strong of an effect. And then the last thing that we also did is because in our case, we basically proposed adding this nonlinear difference of the scores. There are many works on classifier-free guidance that basically propose different techniques. Most of them correspond to having some sort of time scheduler for omega. One thing is that this is still a classifier-free guidance method that kind of falls within like our framework of nonlinear ones. But at the same time, no one's really thought about adding this difference of the scores as far as we're aware. So we could have just said, okay, well, let's just combine the two. And basically we did combine the two and we consistently saw benefits, even adding them on top of previous methods. So for example, we took the limited guidance from NVIDIA, we added the power law guidance to them, which is the nonlinear version. We explored with some other ones and we basically consistently saw improvement in performance, both in terms of FID and some other metrics that basically measure diversity. And that's it. Thank you.
Nice. Okay, then let's see if the chat yields any new questions. I think it's a fine point to lose at least some words on. Can you talk a little bit about classifier guidance and compared with classifier-free guidance, what applies, what doesn't? Should we care about classifier guidance?
Hmm. So classifier guidance, that's actually a very good question. I haven't thought about it because I think that I mean, the whole problem of classifier guidance is that you have to have a classifier that is trained not only on your images, but also like on every noised image for different like values of noise, right? And basically what you're telling your classifier is you're telling, okay, well, what I want to have is I want you to tell me like if this is an image of a dog or a cat, if the image is extremely, extremely noisy, right? And this is super hard. And I think also this is the reason why people aren't doing it. But from a theoretical point of view, we haven't really thought about it because I guess what the classifier guidance would do is maybe help you reduce the error in the estimation of your score. But I'm not sure. I haven't really thought about this. Sorry.
Okay, and then Taha is asking about deterministic samplers and what of your
Do I think the overshoot observation will be less permanent? So we I don't think so. We experimented a bit with this at the very beginning, and I think like the conclusion was the same. Um, Basically, the curves that I've shown were basically averaged over like 1,000 trajectories, and I think that like in theory, like I don't think that it should make any difference because we basically average out this randomness. However, in practice, I think that because DDIM in general sometimes outperforms the standard DDPM, uh, maybe there is also something that is happening because like if the generated distribution is better or like if the FID is lower, means that we're generating something that is basically more similar to our data distribution, which means that there is something that is potentially reducing diversity, but like from a Gaussian or like sampling point of view, I think that would be the same.
okay, what did I want to ask? Ah, right. What does this paper do where you said they use the entropy of the posterior to look at what's going on in the in classifier-free guidance?
So I think basically they have like a whole group like that has multiple papers on classifier-free guidance. I think um, it is I haven't read the paper carefully yet. I think basically I mean you can look at the entropy of basically how sure you are that you're gonna end up in a class. So it is very similar, or basically like in the high dimensional Gaussian analysis, it boils down to exactly the same thing. The thing is, in practice, if you want to analyze entropy, or like if you want to analyze
Yeah.
this, you either need to know the scores really well, which we do not know, which you can see that we do not know them well because if we knew them well, diffusion models would like have no problems generating. But you can look at the entropy as basically kind of a approximation of how sure or unsure you are. So basically, once you see a very big difference in the entropy, um, you can think of this also as the speciation time, because at some point you were not sure and now you're sure.
But
But
so the core question is, you now take this proxy with your mean thing, and then you have your QT as this proxy of the probability of being from class, or the thing being generated from class C.
no,
And
yes.
now, like, how do they actually in practice compute entropy, or in practice compute belonging to a certain class?
Uh, so I'm not sure. I think what they do is like you can just take like a pre-trained like I think if you take
That's
a pre-trained classifier, like it's not going to
okay.
work because you're gonna have a lot of noisy images. But I think what you have to do is what you just have to you have to basically train a classifier that can, like predict what image is it going to be. So you end up doing something very similar
Yeah.
um, to classifier guidance.
Yeah, which we know our noisy classifiers aren't all too good,
Yeah.
otherwise classifier guidance would work.
But I think
Uh,
basically one thing that they analyze is sometimes what they do is like they make sure that the unconditional score is they do like a projection such that like it is orthogonal to the conditional score such that it is giving like a different type of information, or at least like they remove the part that is orthogonal. I'm not sure exactly what they do, but I can send you the link to the group and stuff later, so like for those who are interested, you can give a bit more like
oh,
you can give it a look through.
okie dokie. Any other points from your side?
I don't think so. Thanks so much for this presentation, though.
No
From
worries.
you, Bruno? Anything, any last words before we call it a day?
But there's one question in the chat. Someone asked what would happen if you add the
Ah,
unconditional score. I mean, if you add it, basically what happens is instead of pushing away from the mean of the distribution, you would go exactly towards the mean of the distribution. And I'm not sure if that would basically lead you to anything good. But just one thing, I mean, kind of like that kind of keeps popping up, and I guess like was related to like what you asked me before. Most of these analyses that are like happening at the moment, I think most of them, like including us, we have to assume the perfect score, right? And this is like a assumption that is extremely flawed because like in diffusion models, if you know the perfect score, you will never be able to generalize, right? You will always go back to your target, which is basically the data distribution, like the empirical distribution of your data which you have. And I think many of the reasons why diffusion models work and also why classifier-free guidance works, in order to really explain them, what you have to do is like you have to analyze how big is the difference, or like what is the difference between the perfect score and the estimated score. But I think, I mean, this is like a beautiful research area, like that is open to future work, but is also extremely hard. So if anyone is very interested in explaining exactly why classifier-free guidance works, I think this is definitely the way to go. I think it's super hard, but I think it's also super interesting. So just a comment I wanted to make. I think Mayank, you have a question?
Yep. Hi. I had a question regarding like how the power law on the CFG improves the robustness as well as the image quality and the diversity. I mean, from the standard CFG, these like in the table that you have shown on the paper, so like this kind of increases its uh, like scores. So I was wondering what exactly is the could you point to the exact point like since I think it was the omega uh, that that you changed that corresponded to increase in the uh, performance like, so I was wondering what your thoughts are in this elevation here.
Yeah. So if I can maybe share my screen again. So basically, I guess FID is kind of like a standard metric.
Mm-hmm.
Some people, it's been flawed and stuff, and like there are papers basically saying like why it's flawed. I guess in terms of image quality, you can kind of just think of like FID as basically saying whether the data that you generated looks like the data that you trained on. And basically, what we see, I don't have the plots here corresponding to precisional recall or other metrics of diversity. We also have in our paper, I think, density and coverage, and these are kind of like four standard metrics that basically say whether like your distribution is more diverse or not.
Mm-hmm.
But one thing that I forgot to say, and thanks for reminding me, is just that what we saw across all of our experiments is that basically alpha being larger, so for example, fixing it to 0.9 worked completely okay and beat basically all the standard classifier-free guidance methods. So we didn't actually like after like all these examples, most of the results that you see like in our tables are like basically with alpha fixed. So we
Okay.
did not have to perform hyperparameter optimization. Basically, what NVIDIA people that perform classifier-free guidance in a limited interval, they have to optimize when do they start with classifier-free guidance and when do they stop on top of omega. And basically they see very similar results in terms of increased diversity, increased semantics as us. But on top of that, kind of like the price they have to pay is the same price as we have to pay, is like you have this kind of like additional hyperparameter term. But basically, coming back to your question, the smaller the interval is that you apply classifier-free guidance in, or also the larger the alpha is, which basically means that like you're going to decrease classifier-free guidance when the difference is small. So basically, if the ultimate effect of classifier-free guidance over the whole period is smaller, to have the same benefit, you have to increase omega. So basically, in our papers and in the paper of NVIDIA, you can see that the smaller the period where you apply classifier-free guidance, the larger omega has to be to achieve good results.
Mm-hmm. Okay, cool.
Cool.
Alrighty, then I think we have reached the end of the line of questions. And Bruno, will you be at ICML?
Sorry?
Will you be at ICML?
No, I don't think so. I think I'm trying to reduce my travel. I might come to NeurIPS, but I think for
Okay.
ICML, I'm gonna skip it.
Cool.
Yeah.
Then thanks everyone for joining and see you around, hopefully next week, where we'll be talking with Brandon M. Wood about open mole and the UMA force fields, like the new stuff from Meta. Oh yeah, and this will actually be happening in place at MIT as well. So if anyone wants to join in person over here, then that will also work. Good, see you around.
Thanks a lot.
See you,
Ciao.
Bruno.